Namaste students. Today we will discuss vibration. A 2-degree system is a system which requires two parameters to describe the complete system. In this figure we can see that x and theta are the two parameters required to describe this system. In this figure we can see that k1 and k2 are two parameters given, and x and y are the two parameters required to describe the system. Here we are taking a system of spring mass system. Here two mass m1 and m2 are connected with three springs k1, k2 and k3. Mass m1 and m2 has been excited by a displacement which is x1 and x2. So the free body diagram of these two masses are shown in slide. In m1 mass there is a two spring force k1 x1 and k2 x2 minus x1. Since x2 has been considered as more than the x1, so the difference of x2 minus x1 multiplied by k2 is the spring force acting downward, and the x1 is the displacement provided to the system. Therefore the m1 x1 double dot will the inertia force act upward. So the two equations m1 x1 double dot and m2 x2 double dot are the differential equation for these masses m1 and m2. We have rewritten these equations as shown in this slide. m1 x1 double dot plus k1 plus k2 multiplied by x1 is equals to k2 x2, and m2 x2 double dot plus k2 plus k3 multiplied by x2 is equals to k2 x1. Now we are considering the displacement vectors x1 and x2 as x1 sin omega 1t and x2 sin omega t. Now we will put these two values in above two equations. Then the first equation for mass m1 we will get minus m1 omega 1 square x1 sin omega 1t plus k1 plus k2 x1 sin omega 1t is equals to k2 x2 sin omega 2t by putting the value x1 double dot, x1 and x2. Therefore the ratio of x1 and x2 will be equals to k2 sin omega 2t divided by k1 plus k2 bracket minus m1 omega 1 square and whole bracket multiplied by sin omega 1t. Let this ratio sin omega 2t to the sin omega 1t is a constant. This value will come as 1. It cannot be more than 1 or the less than 1. So the sin omega 2t and sin omega t ratio will be equals to 1, will give us the omega 1 and omega 2 as equal. So when we are considering omega 1 and omega 2 equal, we will get x1 equals to x1 sin omega t and x2 equals to x2 sin omega t. Now the omega 1 and omega t is replaced by omega. Therefore the two equations for mass m1 and mass m2 will be rewritten as minus m1 omega square plus k1 plus k2 multiplied by x1 is equals to k2 x2, and other for mass m2 is shown in slide. So the ratio of x1 and x2 will be k2 by k1 plus k2 minus m1 omega square. For the second mass, x1 by x2 equal to k2 plus k3 minus m2 omega square divided by k2. Now these are the two ratios x1 and x2 from both the equations. Now we are equating these x1 by x2. We will get k2 divided by k1 plus k2 minus m1 omega square is equals to k2 plus k3 minus m2 omega square divided by k2. So by cross multiplication we will get equation m2 omega square minus m1 in bracket k2 plus k3 plus m3 k1 plus k2 whole bracket is multiplied by omega square plus a factor k1 k2 plus k1 k3 plus k2 k3 is equals to 0. So this is a quadratic equation of omega square. This will give two values of omega n1 and omega n2. These are considered as the two natural frequencies of the system, omega n1 and omega n2. Now we are considering a special case when the first spring and third spring, we are considering the stiffness k1 and k3 are equal, that is equals to k, and the mass m1 and m2 are equal, that is equals to m. Now putting these value in the below equation, we will get, since m1 and m2 are equal, so m1 it will become m square omega 4 minus 2m k plus k2 multiplied by omega square plus k square plus 2k k2 is equals to 0. So now we will get two values of omega n1 and omega n2. By this is a quadratic equation of omega square, so we will get omega n1 and omega n2 as under the root k plus k2 plus minus k2 divided by m. For considering plus sign and considering minus sign, we will get two values. So the natural frequency of the system omega n1 equals to under root k by m, first natural frequency, and second is under root k plus 2k2 by m. So these are the two natural frequencies of the system. So by putting the constraint k1 equals to k3 equals to k and m1 equals to m2, we will get the ratio x1 and x2 from the both the equation as shown in slide. X1 and x2 equals to k2 divided by k plus k2 minus m omega square, and x1 by x2 equal to k2 plus k minus m omega square by k2. Now we will put the value of omega square from above. The omega square is k by m and second omega square is k plus 2k2 by m. We will put these two values, then we will get the ratio. By putting for omega n1 k by m, we will get x1 by x2 mode shape is equals to plus 1. This means when the system is vibrating with the first natural frequency omega n1, that is under root k by m, the mode shape is such that the ratio of the amplitude of the two masses is equal to plus 1, and suffix 1 is showing first mode shape, the first mode shape corresponding to the first natural frequency. Similarly, now we will put the second omega n2 in the equation, and we will get x1 by x2 equals to minus 1, which means the system is vibrating with second natural frequency omega n2, and the mode shape is such that the ratio of amplitude of the two masses is equal to minus 1, and suffix 2 is showing the second mode shape corresponding to second natural frequency of the system. The ratio of amplitude of masses being plus 1 means the amplitudes are equal. plus 1 means x1 is equals to x2, and two motions are in phase, that is two masses are moves up or down together. Whereas when we are getting minus 1 means that the amplitudes are equal but the two motions are out of phase, that is mass 1 is moving up and second one is moving down, or vice versa. So we have seen that first natural mode vibration, the mode shape is given by x1 by x2 plus 1, and second mode shape is given when the x1 and x2 ratio is equals to minus 1. So in this figure we can see when the first mode shape, when omega n1 is under root k by n, it is considered as the second spring is not acting at all and x1 is equals to x2. This mode shape is given x1 is equals to x2. If the two masses are given equal initial displacement in the same direction and released, then they will vibrate in the first principal mode of vibration with the first natural frequency, that is omega n1 equals to under root k by. Similarly, for ratio x1 by x2 equals to minus 1. Minus 1 means x1 is moving in one direction and x2 is in opposite direction with the same amplitude. If the two masses are given equal initial displacement in the opposite direction and released, then they will vibrate in second principal mode of vibration with second natural frequency, that is under root k plus 2k2 divided by m. Thank you.